All right, I guess we should dive in. Towards inference. We often want to know, excuse me, want to answer questions about a population but it isn't feasible to collect the data for an entire population. This isn't a new idea. We've talked about it before. It was the whole reason that we introduced this idea of a sample. We don't have the resources to collect every single data point for a population, so instead we look at a sample and we use the sample to say things about the population. And this latter little point is what we call inference. But let me motivate it and motivate all of this stuff with an example. Suppose the average heart rate and I'm going to use beats per minute, BPM, as my measure of heart rate. But the average heart rate for an octopus is distributed uniformly with unknown mean mu. Also, side note, octopuses, some of them have 3 hearts, so I mean the first of their 3 hearts. Small nuance. As mentioned, we can't capture every single octopus in the world and measure their heart rates. So, how do we guess at mu? And I'm just going to tell you that a natural choice, and I hope, I find it intuitive, I hope you do as well, but a natural choice is to take a random sample of all possible octopuses, so a simple random sample, and calculate the sample mean, which we often denote x bar. So the picture here, why don't I do this? And this was a picture that they actually drew back when I took my very first statistics class. So I'm passing it now on to all of you. And that is, you have this population, so it's a huge amount of numbers, which I'll call octopus BPM. And imagine there's just like a bunch of different values, a bunch of different octopus with a bunch of different heart rates. And one of them is this unknown population average mu. And the idea is, if we could capture every single octopus and calculate every single heart rate, we could calculate the average, we could add them all up and divide by the total, and we could get this true value that is out there, mu. But as mentioned before, it's not feasible for us to hard calculate mu. So what we do instead is we take a sample. So let me see if I can, looks like this, right? We take a sample, and from the sample, we calculate x bar, the sample mean, which, we know how to do this already. It's just 1 over n, the size of the sample, sum of all the values divided by n. And then we use this value. I'm going to do this in another color. We use x bar as our best guess at mu. And this step right here, this using our x bar to make a best guess, that's what we call inference. And it's one of the more sexy things we do in statistics, because it is like, what is the most mathematically accurate guess at what the truth is? So note is that we call the sample mean a point estimate of the population average. It is a singular value that is our best guess. So this is the basic idea of inference, and we often use the example of the sample mean. But there's an important note about all this. And that is, say that I took a sample of octopuses. I somehow was able to determine, okay, this is the population of total octopuses, and I'm going to randomly choose 20 of them. So this is the heart rate of the first octopus. This is the heart rate of the second octopus, all the way down to the heart rate of the 20th octopus. So I took a sample of size 20, and I can take all of these values, and I can calculate 1 over 20 times the sum of all of these heart rates, right? This is just equal to x bar. And indeed, this would be my, or our, best guess at mu. But wait, I took a sample of size 20 and I calculated x bar. What if we did this again? I took another sample. I threw all my octopuses back in the ocean, and I took another sample. And it was another sample of 20 octopuses. But note that these are potentially 20 different ones, right? I took another sample. I mean, maybe, very unlikely because it's a huge population, but maybe one of them is in my sample again, sure. But the point is, it's not going to be the same sample. I'm getting a bunch of heart rates that are all potentially different from my first sample. But I still picked them randomly, and I can still do this calculation. Sum them all up, divide by 20. And I get another sample mean, another x bar. And I'm going to put a little star here to note that it's different. In fact, we wouldn't expect it to be the same because it was a different sample. But note, this is also our best guess at mu. So note that with a different sample, we'll get a different sample mean. We would not expect x bar and x bar star, these two sample means from our two samples, we would not expect them to be equal. So the key idea here, and the thing I'm going to try to motivate for the remainder of class, is that the sample mean is itself a random variable. It can take many different values with varying probabilities. All right, so I hope we can see that at least, that with a different sample gives us a different x bar. And since we're choosing these samples randomly, we could get a bunch of different x bars depending on which samples that we randomly pick each time. And that's sort of the next idea, is that, so we did 2, what if we did many? If we took many samples of size 20, well, oh my goodness, I'm gonna have to come up with new symbols. Let's see, I think I have a hashtag, so we'll say that this was from my first sample, x bar hashtag, from sample 1. And then I think I have an x bar star again for sample 2. Took another sample, got x bar actual star, sample 3. Took another sample, got x bar crescent moon for sample 4. Got another one, x bar smiley face for sample 5. And so on and so forth. And I'm gonna put a zeta here, but I'll come back to that. So I could take a bunch of samples, I could get a bunch of x bars, and what is a natural next question is, so we could then ask, questions like, what is the average x bar? Right? Because I'm getting a bunch of different values for x bar, and I can do it again and again, and I'm going to get a bunch of slightly different values every single time I take a sample of size 20. Well, what is the long-term average? If I were to do that an infinite amount of times and average them all together, what would all of those x bars average out to be? I don't know, but I also do, so we'll talk about it. This is equivalent to asking, what is the expected value over the long term of x bar, right? We could also ask, what is the variation of x bar? Right? So we want to know its long-term average. What if we got a ton of x bars? How much would they vary? Would they vary a lot? Like, would there be values that were like 1 and values that were like 3,000 for heart rate, which wouldn't really make sense? But or would they have a small amount of variation? And this is equivalent to asking, what is the variance of x bar? Okay. So we call the probability distribution of X bar. Oh goodness. I do not know how to get rid of this. There it went. We call the probability distribution of X bar the sampling distribution. Of size 20. And I'm actually going to show you a picture of it. So recall what I called eta, which were all of these different X bars, right? I took a sample of size 20, got an X bar. I took another sample of size 20, got an X bar. Well, if you were to do that again and again and again and again, you would get a ton of X bars, and you could express the distribution of all of those X bars. And that's actually what this is. This is, so it looked like X bar was, oh goodness, what is this, like 93 or 92 and a half? It looks like it was around 92 and a half about this many times, if I did it a ton of times, right? It was 94, 95 the most often, right? It would appear. And there were values up in the lower tails and the upper tails as well. So X bar will actually itself have a distribution, and we call that distribution the sampling distribution. And we can think of every value of X bar, and we'll say from that, from up here, every single value of X bar from up here, as a random draw from the sampling distribution. Okay, and I'm going to show you a little bit of a simulation, and I'm unfortunately I'm going to sort of have to switch back and forth here. But I want to show you the first of two things we're going to look at today. Here. So this simulation, it actually wasn't written by me, it was written by a colleague of mine, Dr. Karlstein. And what you are looking at here is, I have a ton of data values. So what you see in the gray on the right here, that I'm just going to put away, are just so many different, they're actually from a uniform distribution, but you don't really need to know that. But pretend I went out and found this many octopus. This is the, you should look at this as the whole population of octopus heart rates, right? Somehow somebody went out and measured every single frickin' one, and it's in this spreadsheet. Holy crap. And what this spreadsheet is doing is every single one of the, it's going to these gray values, it's taking a sample of size 20, calculating the sample mean, just like we did, and it's putting that sample mean as a green line on this graph. So every single one of these green lines is a single sample mean that we just graphed, right? And you can note that they vary. They go up and down, right? And they vary above and below this orange line. And this orange line actually, and I'm telling you this, we don't always know this in the real world, but in this very special case, since I had all of the data here, I calculated what the true value was, the true mu for the whole distribution, and I put it right here on this orange line. And what this means is it seems like even though the sample mean is varying up and down, it seems like it's varying around the true value, the true mu value of my whole population. So this figure might not make 100% sense to you, but the thing to notice is that I can take a bunch of samples and I can get a bunch of those green lines, and they vary, and it looks like they vary around the true value. which is a very interesting fact, and I'm going to show you more about that in a second. All right, so let me go back to sharing. So I have a couple of facts about the sampling distribution. One is that the expected value of x, so the long-term average of these x bars, is actually equal to long-term average of x, or otherwise known as the population average. So this is a very interesting fact, actually. It answers the question I asked at the very beginning. What if we took a ton of x bar values? What would we expect sort of the average x bar to be? And the answer is it averages out to the truth, to the true population parameter. And that is a very important fact about this that we are going to be using a lot. The other question is, the other fact I'm going to give you is, what is the variance of x bar? And that is also related to the true variance of the true population variance, right? Because if I took every single octopus heart rate, if I had every single one, I could plug it into my variance formula and I could tell you what the population variance is. Well, since we can't calculate every single octopus heart, we can then instead look at this relation, the variance of the sampling distribution's variance, the variance of x bar, is actually just equal to the true variance of x divided by, not root n, divided by n, which is just equal to sigma squared, where sigma squared is the true population variance. And 3, and this is the most important thing I'm ever going to tell you. Ooh. The sampling distribution of the sample mean x bar is approximately or I want to say approximately follows a normal distribution. And this is this is likely one of the most profound results in statistics and actually all of applied mathematics. And it is a consequence, or I should say, of the central limit theorem. And let me see, have any of you ever heard of that before? Has that name ever come up on your radar? The central limit theorem? Maybe some of you? Well, it is actually, it's going to be the topic of my upcoming lecture video, and it's likely the most theoretical we get in this class, and it's something that we need to use, absolutely, but I hope to, if I give you anything, it's just a mere intuition on it. I don't actually give you the very precise mathematical definition of it, but you should at least know what it is to be statistically literate, which is probably one of the goals of this class. So, this third fact, the sampling distribution follows a normal distribution. To better explain to you what that means, we are actually going to do a class activity. I hope you're all as pumped about it as I am. So let me share my other screen. So what we see here, this is left over from my last class, 1 second. What we see here in yellow are a bunch of random values of an unknown distribution. So I haven't necessarily said how I got these values. Maybe they're octopus tentacle links. I don't know. But I got a couple hundred, and this is my data set. Pretend this is all of the data that I have. And note that this histogram is the histogram that I built off of these data values. So it's clearly not normal. It looks about uniform. This data, it's looking pretty uniform. I'd have to like go through and determine whether or not it truly was. But here's my data set, and what I want us to do is I want us to, every single one of us, choose as randomly as you can 10 values from this data set in yellow and calculate the mean of those 10 values. So take all 10, add them all up, divide by 10, and then shout out your number to me. I can't quite see the chat if I'm gonna input them while you shout them out to me, but so help me out and actually speak them. And once you calculate the first, go ahead and calculate a second, because I don't think we have quite enough people to fill this whole bar, and I really want to fill the whole thing. So let's see what we get. I'm so excited.
I got 61.28.
61.28, first one. Very nice. Thanks, Violet.
I got 63.62.
All right. Very nice.
I got 58.08.
58.08.
66.66.
Oh, how ominous.
64.32.
Okay, I heard 64.32. Was there another one?
58.72.
58.72. Thank you, Con.
58.07.
Was that 58.07?
Yes.
Right. 58.07. Thank you.
Yeah, 60.4.
60.4?
60.04.
Nice.
I got 61.01.
0.01. Very nice.
I got 64.27.
0.27. Thank you.
I got 61.1.
Okay, both of you spoke at the same time.
Sorry.
I got 58.1.
58.1. Okay.
And I got 61.1.
61.1. Okay.
60.47.
Okay, once more.
60.47.
60.47. Thank you very much.
Mm-hmm.
I got 61.4.
61.4. Okay.
I got 64.37.
37. Okay.
I got 62.71.
62.71. All right. Thank you.
I got 63.98.
3.98. Very good.
I got 60.93.
60.93.
I got 60.94.
60.94. Okay.
I got 62.15.
Okay.
I've got 59. I've got 59.72 and 62.88.
Very nice. All right, I think I need like, what, 5 more?
61.23.
61.23?
62.29.
62.29, thank you.
65.12.
65.12.
I got a 60.73.
All right, one more.
I got 60.89.
Ah, Kate, bring it home. Thank you. Okay, so we took a bunch of samples of size 10 from these yellow values, right? And we calculated a bunch of sample means, and I have graphed them right here on this histogram. And there's something pretty interesting to notice is that the distribution of x, the distribution of our original values, does not look like the distribution of our x bars, right? One looks very normal, and this one, we'll call this, should name it, R section 5's sampling distribution. Okay. Oh no, there. Okay, so this one on the left looks like very much uniform, but this one on the right is starting to look a little bit bell-shaped. And that's the marvelous thing, is that by the central limit theorem, if we were to keep taking values, keep taking x bars, they would more and more so be approximated by a normal distribution, a bell curve, no matter what the distribution of our random values were. So we took a bunch of random values that looked like they were from a uniform distribution, but we could have taken a random value from anything, and it could be distributed in any way. And if we were to do the same thing, take a bunch of x bars and put them into a histogram like we've done here, they'll start to look bell-shaped, which is like, okay, this is you might not be that excited about, but this is actually supposed to be one of the most used results in applied mathematics, and probably it definitely is in statistics. So it's so exciting. So one other thing I wanted to mention before I move off of this picture is, where's the center of this histogram? Where would the expected value of x, what do you think the average would be? Usually, when we think of it in terms of histograms, it's like the balance point of wherever the histogram is. And I'm seeing, it looks like it's like around 63, 64, maybe. Do we see that if we're looking at the uniform? Well, where would the balance point be here? What would the average be over here? And the answer is, it looks like it would be about the same. It looks about 63, 64, somewhere in here. So the thing to notice is, these distributions, they look very different. One is looking kind of uniform, one is looking kind of normal. But they are centered at the same place. And that place where they are centered is actually the true average, if I were to take all of the averages of my entire population. So that's how everything's kind of connected here. I'm going to put this Excel sheet on the Sakai page, so if you want to have as much fun as I've been having with it, you're more than welcome to. So that is our central limit theorem activity. Let me stop sharing. Are there any questions before I put this away? Okay, cool. I'll switch back to my iPad. Okay, so we have these three facts: that the expected value of x bar is equal to the expected value of x. We have that the variance of x bar is related to the variance of x, but it's not quite equal. We have to divide by n. And we have that the whole thing is normally distributed. So let's do some examples about how you would actually use these three facts in a problem. So, example. Excuse me, I'll get some water. Using our previous example with octopus hearts, say we took a simple random sample of 20 octopuses where the distribution of octopus hearts, of heart rates, is uniform, with the lower bound being 80 beats per minute and the upper bound being 110 beats per minute. What is the expected value of X bar? What is the variance of X bar? And also the standard deviation. Okay, let's do it. So the expected value of X bar is just equal to the expected value of X, which is an expected value, so of a uniform. And we had a formula for the expected value of a uniform distribution, right? It was A plus B over 2, which in this case is 80 plus 110 over 2, which is just 95 beats per minute. So the sampling distribution of X bar is centered at the same place as the distribution of X, which is 95 beats per minute in this case. The variance of X bar is just equal to the variance of whatever our data are divided by, oh, I keep trying to do that, divided by n, which is just equal to whatever the standard deviation is divided by n. And we had a formula for the variance of a uniform. Remember, I think it was, I know it was, b minus a squared divided by 12, right? And we want to divide that whole thing by n. So what is that going to be? It's going to be 110 was our lower bound minus 80, our upper bound, squared divided by 12. And our n in this case, we took a sample of size 20, right? So this simplifies to 30 squared over 240, I believe, which is 3.75. This is variance, so it's beats per minute squared. Okay. And standard deviation is not that hard either. It's just going to be equal to the square root of the variance of X bar. And actually, I'm going to show you this little algebra here. It was confusing some people in my last class, so I'm going to write it out a bit more. Right, the variance of X bar is just equal to this, so I'm plugging it in here. And by algebra, it's equal to that, which is equal to, well, variance of X is just equal to the standard deviation of X over root n. Yeah, so standard deviation of X bar is actually equal to this, standard deviation of X divided by root n. But similarly, we didn't have to go through all of this. We didn't have to go through all of this algebra since we already had the variance of X bar. That's just equal to, what was it, 3.75? Boom. Seems a little bit easier to me, but I think some people have seen this formula from other statistics classes, so I wanted to at least put it up there in case you were like, oh, why is he dividing by n and not dividing by root n? This is why. You divide by root n when you have standard deviation, you divide by n when you have variance. So we have the square root of 3.75, which is 1.9365 beats per minute. Very nice. So we know our mean and our variance for x bar. And we also know that x bar is distributed normally. So x bar is distributed normal, centered at 95, with a variance of 3.75. Boom. That's how we use our three facts. We can say exactly what the distribution of x bar is, which is going to come in handy when we start talking about hypothesis testing and confidence intervals. So I have another example that that hopefully illuminates a little bit more about the variance of x bar. So what if we did the same thing but instead took a sample size 30, right? So now I want to know the sampling distribution, not if I'm taking samples of size 20, but taking samples of size 30. So I'm taking larger samples. Well, E of x bar here is still just E of x, or mu, which we know as 110 plus 80, because our underlying distribution is uniform, divided by 2, or 95 beats per minute. So changing your sample size, it's still going to be centered at the true value, so that doesn't change anything here. What about for the variance? Well, we said the variance of x bar was this, right? The true variance divided by n, and our n is increased here. So let's give this a shot. Let's say, so we want the 110 minus 80 squared over 12 because it's a uniform. The data is uniform. The data is uniform. Now we're going to divide by 30, which is going to be 30 squared 12 times 30, I believe. I didn't actually calculate this yet, so let's see what it is. It is 30 squared. And it looks like it's going to be 2.5. And thus, the standard deviation of x bar is the square root of that, which is 1.58113888 beats per minute. Oh, this one's squared. Okay, so something to notice. And that is when your sample size was equal to 20, our variance is equal to what? It was 3.75? When the sample size was equal to 30, variance of x bar was 2.5. So when we took samples of size 20, the x bars that we found were more variable, they were more spread out than when we took a larger sample size. Taking a larger sample size actually squeezed the values in and reduced the amount of variation. So larger sample size means less variation. We can actually see this in that first simulation I did. I swear, this is the most I switch back and forth of any class I do this semester. So recall this picture. So we have a ton of data values, a huge population, and we're taking samples, in this case, of size 20. And our green values are the different values that we get for X bar. So it's our sampling distribution above and below the true value, the mean. Now, what I'm going to do here is I'm going to change this value n. And when I do so, instead of taking samples of size 20, I'm going to take larger samples. Before we do, let's make a comment on how these values are varying. It looks like they're kind of spread out. They're definitely centered above and below the true value, the orange dotted line. But they vary. Let's see, this one looks like this one's all the way up at like, oh crap, it's like 102, 101, right? So there's one up in 101 and they go down to about 91. So our values are varying between 91 and 101 here, right? Do we see that? Now watch what happens when I increase the sample size. And watch the y-axis here, because it's going to renormalize. So I'm going to up it to, let's do a really large sample, 200. Notice what happened. The y-axis renormalized and got smaller. And now our values are varying between, it looks like this is 92, 93 to about 99. The variation's squeezed in. Our values all squeezed in towards the mean. And what this means is if you take larger samples, you have a lower variation, which basically means your values are still varying about the mean, but they're varying closer to the mean. And actually think about it, if you took larger and larger samples, they would vary closer and closer to the mean until your sample size is so large that you just have the entire population. So you just have the actual mean, right? So that's one of the things that's going on here. We have our sampling distribution is centered at the true value, and the larger sample size you take, the closer those values vary around the truth. Which is, this is the new theoretical idea, and we're going to be using this to do inference. So let me switch back. Where am I at? Let me see. So we got through things a lot faster than I did in my last class. Are there any questions? No, all straightforward. This is the most difficult lecture, so there are no questions. You all are doing really well. Okay. So if there are no questions, I'm going to give you this extra time to do your quiz. And also, this is a little bit longer of a lecture video, so I don't feel bad ending a little early. Let me, here, I'll first give you this. The quiz code, and let me go on and open it up for you. So Cengage was actually down a little earlier today. So I'm hoping they've figured their crap out a little bit and we're able to take the quiz. But let me know if anything goes awry. All right, it should be available. So if you refresh your screens, I hope you can see it. Thanks.